But today we are going to mainly focus on the free convection, and we will compare it with the forced convection. Up to now, what we had was using some kind of pump or fan, or even something like a wind, which is a forced convection. The flow was has a external stimuli that can push the flow around the object. But the free convection is different, and we will see how we can calculate the convection heat transfer with this method. First, let's see how is this physical mechanism of the natural convection. As you know, in many transfer applications, we have this natural convection. Natural convection means we don't have any pump or fan. Like TVs, you know, your TV actually has a natural convection. It doesn't have any fan, but because it is an electrical device, it produces heat. So there is some devices to cool it down, like a sink, but heat sink is not doesn't have any fan. Like heaters, like steam radiator, like refrigeration coils. All of these are your everyday devices which you are using them, and they involve this natural convection. And one interesting example is your meal. Your hot meal, like a hot egg, is cooled down by this natural convection. The motion from the continual replacement of the heated air around the egg by cool air is called a natural convection current. These currents around the egg, these arrows actually are showing the current of the convection or heat transfer. We call them natural convection current. You can see this is hot air and it moves upward. We call that natural convection current. And the heat transfer that is enhanced as a result of this current is called natural convection heat transfer. Due to this movement or current of the hot air around the egg, the heat transfer is occurring, and this heat transfer is called natural convection heat transfer. So this is a simple example of the natural convection. As you can see here, there isn't any fan, any pump to move the air. You know, do you remember the first condition to have convection? The air or the fluid should be in movement around an object, and there should be temperature difference between them. As you can see here, we have hot egg. Its temperature is higher than its air around that, so we have temperature difference, and the air is in movement. But this current of the air or the flow of the air is not by the pump or fan. But why the air is in movement, why it has a current like this, we will see in next slide. What is the reason of the movement of the hot air to upward, for example, here? Actually, the buoyancy forces are responsible for this fluid motion in natural convection. I don't know if you remember these buoyancy forces. It comes from the fluid dynamic actually. If you remember from your fluid dynamic subject, this part may be just a repetition of the buoyancy forces. The buoyancy force is the force which comes from the fluid to any object which is merged or submerge actually through that. This force can be calculated by this equation. Buoyancy force is equal to density of the fluid times the gravitational acceleration times the volume of the body. For example, this is a ship. You can see here it is floating in the water, in the sea, for example, and it is floating. Why it is not merged completely and sink into the sea? Because of this buoyancy. The buoyancy is against the weight or the gravitational force of the ship. So the buoyancy force can be calculated by this equation. And so the net vertical force acting on a body like this can be calculated by this equation. The buoyancy force is subtracted from the weight of the body. The weight of the body is can be calculated by this equation. Its density, actually this is MA. If you remember, this is the Newton law for the movement, the first law. This is MA. Rho V here is the M of the body times G is mg. So this is F, which is downward, and buoyancy force, which is can be calculated by this equation, which is upward. So finally, it depends on the difference between the density of the body and fluid, this movement. So for a solid body like this buoyancy is almost constant during the time. But when the object actually, this object is a fluid like air, it's a little different. The temperature of the fluid is effective. As you remember in previous lectures, the fluid is made by different layers. So when the density of each layer changes, it may goes downward and upward due to this equation. Why? Because when the temperature of the fluid, in that case we have rho, for example, rho of hot fluid, rho of cold fluid, for example. We have this equation is changed. We have layer of the fluid. So the difference between the density of fluid in different temperature is cause for this F net, or the movement of the fluid, which is due to the volume expansion. You may have experience about this. When the volume or when the temperature of something is changed, its volume also changes. Something, I mean the compressible fluid like air. When its temperature is changed, its density also is changed. Its volume is changed, then its density is changed. This change can be defined by the equation which we call that volume expansion coefficient, or beta. This beta is equal to 1 divided by V times del of V divided by del T. V is the volume and T is temperature. This term means change of the volume by change in the temperature. As much as the change of the volume of the fluid is higher due to the change in the temperature, its volume expansion coefficient is higher. I just repeat that. With change in the temperature, the volume of the fluid, compressible fluid, is changed. If the change in its volume is higher, it means that its volume expansion coefficient is higher. You can see here a substance with a large beta or volume expansion coefficient. You can see its volume is changed too much. Just temperature is changed from 20 degrees Celsius to 21 degrees Celsius, but its volume is changed this much. Is a huge amount almost. But a substance with a small beta or volume expansion coefficient, its volume is changed just a small amount by changing of this the same temperature from 20 degrees Celsius to 21 degrees Celsius. So as you can see here, the volume of the substance, which usually for the gas substances, we can see this phenomenon. So with changing the temperature, their volume is changed. The change in the volume means changing the density, and changing the density means changing the buoyancy forces. So we can use this volume expansion coefficient to see how the density is changed, then how the buoyancy forces changes, and finally to understand how is the movement direction or the current direction of the fluid. At constant P, as you can see here, also the pressure is also effective on the volume, but here we imagine P is constant. For the natural forces, natural convection, usually P is constant. For example, we had an egg on the table. The pressure is same, the pressure doesn't change. Only thing which is caused for that current of the convection or thermal current is the change in the temperature of the air around that. The air around the egg, let's go back to here, air around the egg is heated, its density is lower, then it will go up, and cold air will come down near to the egg, and this will happen until the temperature around the egg of the air around the egg is same as the temperature of the surface of the egg. And at constant P, we can write this equation. Beta is almost equal to -1 by rho, delta rho divided by delta T, which delta, this is for this beta is when we have constant constant pressure. By rearrangement of this equation, this is change of the density due to change of the temperature. By substitution by rearranging this equation, we can write the rho infinity minus rho equal to rho beta T minus T infinity. Beta is a value which we can find for different material or substances. So it is dependent on the temperature. For the temperature which we should find this beta is T minus T infinity, for example. T infinity, as usual, is temperature of the fluid enough far from the surface, and T is the temperature of the object. And for ideal gas, we can write this equation. Beta for ideal gas, or volume expansion coefficient for ideal gas, is equal to 1 divided by T, which is the temperature of the fluid. So we can, for ideal gas, usually for many cases we have ideal gas. For the natural convection, usually we have the air. Air is ideal gas, and so we can use this equation in many problems. We can find the beta or volume expansion coefficient by this equation, which is inversely proportional to the temperature of the substance. Okay, now we know what is the reason for the movement of fluid near the surface. And this is just a repetition of what I told you. In natural convection, no blower are used, and therefore the flow rate cannot be controlled externally. The flow rate in this case is established by the dynamic balance of buoyancy and friction. So imagine this is a surface, vertical surface actually. From now on, something is interesting for the natural convection. Usually we have a vertical flow because already know about the buoyancy. It is a force which actually it is interaction between the density and the gravity. These two are effective on the flow in a natural convection. So imagine this is a vertical plate and this is the flow on that. You can see different layers of the fluid on the surface. And as usual, we have a buoyancy which is upward, and we have a friction between the fluid and the surface, which is a resistant force against the flow. So the flow rate can be calculated by the balancing of the buoyancy and friction forces. And you can see here, and also one more interesting thing about this convection, we have again laminar and, as you can see here, turbulent flow. It is different from what we had for the forced flow, but again we can calculate when we can have the when we have laminar flow and when we have turbulent flow. For the external flow, for the forced flow, we use the Reynolds number. If you remember, we use Reynolds number to calculate to see if the flow is laminar or turbulent. What about the convection? Can we again use that Reynolds number? No, we should find a new value for that, because here actually the velocity is different. Fluid velocity is not one of our parameters, for example. And we will see, and also as you can see here, one different from this free convection or free flow is that usually it is in contact with the surface just from one side. You can see this is the plate and this is surface of that, and this is fluid, different layer of the fluid. And this black line actually is the isothermal layer. The temperature of that is same as and you can see how is the temperature. Here we have fully developed temperature. The temperature is constant after this. Okay, now let's see how we can understand if the this free flow is laminar or turbulent. First, we should find the equation for that. Imagine this is a vertical flat plate, and this is the fluid flow or stationary fluid. The fluid comes due to that buoyancy forces touch the approach to the surface, then its temperature in boundary layer means the temperature of the fluid near the surface is changed like this. This is the temperature profile. You can see here temperature, here we imagine that the temperature of the surface, vertical surface, is higher than temperature of the fluid. So its profile will be something like this. Temperature near the surface is temperature of the fluid near the surface is same as the temperature of the surface, and it will be lower when we go far from the surface, and it will reach the temperature of the T infinity, which is the temperature of the fluid enough far from the surface, or stationary fluid. The fluid here is not in movement actually. So this is the profile. You can see this is different also with the forced flow. It is in just one side in contact with the surface, and also its velocity profile is like this. Velocity of this fluid near the wall is 0. It is increased, and at the center, almost center of that profile, this is profile or boundary layer of the fluid, almost in center of that will be the maximum, and enough far from the surface, it is again its velocity is 0. So this is the profile of the fluid which is in movement. This is its velocity profile, this is its temperature profile. Okay, now we can see this figure. Now let's to find the appropriate equation for that. First, we should find the forces which are acting on a gradient volume of that fluid. For example, we can choose the gradient of this fluid. This is this one, for example, but near the wall. What are the acting forces? Here are the acting forces: shear force, the pressure, which is due to the buoyancy force, and also the weight of that differential volume. How we can find the equation of the motion that governs this natural convection flow? By writing Newton's second law of motion. If you remember, in x direction, here x is vertical. This is also important. X is vertical, so fx is equal to ma actually, but here is the gradient, so delta m dot ax, or the acceleration in x direction. Its mass or the time is its density times its volume. Its volume can be calculated by this dx times dy times z, but toward out of the screen, which we can imagine it is unit. So its volume, its dx dy, this should be dz actually, but we can imagine it is for unit of the length, so dx dy times 1. This is the mass. So we have mass. What about the acceleration? The acceleration in the x direction is obtained by taking the total differential of ux and y. Ux and y means relative velocity in x and y direction. Or we can write ax is the differential, you remember this equation, differential of the velocity per time, change of the velocity by time is the acceleration. By substitution of this, we should use this equation. This is the partial differential equation for x and y. This is mathematics. You can find it how to write differential equation for the when you have two independent parameters. So finally, this rho u by rho x or dx by dt is again u. This is again a speed, it's u, and the dy dt, change of the distance with time, differential of the distance per time is again velocity. This is velocity in the x and y direction, and rho u rho x again is the acceleration. This is just mathematics. Then the net force which are acting in the x direction, we can again go back to our equation, fx equal to ma or delta m dot ax. Okay, and also from the figure you can see what are the acting forces in x direction. You can see the acting forces in the x direction are tau plus rho tau by del y dy minus tau. In this direction, this should be minus this. We have only this. You can see this, which is times dx1, the surface. The surface which this force is acting is it is this surface actually. This is like this figure. If I am going to make it more clear for you, so this is acting on this a. Okay, if I write a tau is dx1. What about the force in on this surface? P plus rho p rho x dx p. This minus this, we have only this pressure acting on this dy times 1. This is 1, the size is 1. This is z. We imagine this is unit, which is 1. So it is 1 times dy. So rho p rho x dx, this one, pressure acting on this. This is upward. Up is positive. This is upward. This is downward. And we have the weight also for that. Rho g, or the mass of that, the times its volume. This is the weight of this differential value. By rearrangement, you finally have this equation. This is the force in x direction. Then we are going to make that equation, which is this one, more visible and more simple to be used in our calculation. Up to here, we only found the force. Okay, we found the force. How is this force for the fluid in the boundary layer? Okay, this is the force in that direction. Okay, now by substitution above equation, in the equation 1, this is fx if we substitute in this equation, and dividing the both side by rho dx dy1, which is the which we are going to make it more simple. The equation it will give us the conservation of momentum in x direction. Okay, so we put this is fx, we put this in this equation, then divide this, this is this equation have both sides. This is ax, we should put ax here. This is ax, this is delta m, we should put ax here, put delta m here. We found fx, we should put here. Then if we divide the new equation, which is formed by this parameter, we will have this equation. By divide that equation to rho dx dy times 1, we finally get this equation. And for the x momentum equation for in the quiescent fluid at the outside of the boundary layer, it means here outside of boundary layer where u is 0, this equation will simplify to this. So for the fluid outside of the boundary layer, we have this equation. Why we are going to use this? Because this is one of the boundary condition, and we can use that to solve this differential equation. By when we put this rho p infinity by rho x equal to rho minus rho infinity g in the equation here, for the outer or the out of the boundary layer, if we put this in this equation, when we have at the boundary layer, we can find this. Then by substitution this negative rho infinity g, we can write something like this. Imagine this is rho infinity g minus rho g. We can write it like this, plus rho infinity minus rho times g. So understand why we have something like this. Why we write this like this? Because we are going to use the definition of that coefficient we had for the volume expansion. If you remember, this is volume expansion coefficient at constant p. Constant p means out of this boundary layer, so we can substitute this, we can bring out this term from our equation, then write this final equation, which is this is the equation that governs the fluid motion in the boundary layer due to the effect of buoyancy. So this is the final equation. This is the final equation which governs the motion of the fluid at the boundary layer due to the buoyancy. But the complete set of the conservation equation, we just repeat them here for continuity, momentum, and energy that govern the natural convection flow over vertical isothermal plates are this equation. For continuity means the related to the speed of that, momentum related to the momentum of that fluid flow, energy, how is energy is changing, and also we have these boundary conditions at y equal to 0. Y equal to 0 means at the surface ux and y0 here is 0. Velocity here is 0. And also Vx0 is 0. So velocity at this point actually is 0 in both directions. And temperature at this point is also, temperature of the fluid at this point is equal to temperature of the surface. And also at y infinity means on this line actually, y is infinity, u is again 0, this is velocity profile, the velocity is 0, and v is also 0, so because it is a stationary fluid. But the temperature on this line is T infinity, or a temperature of the fluid far from the surface. These are our boundary conditions. Then can we use that equation to understand if the fluid flow is laminar or turbulent? No, still we have many differential parts, so you should find a more simple equation. So we introduce the Grashof a new number like Reynolds number. Actually, Grashof number is the number for the convection or free natural convection. It's similar to Reynolds number, but for the natural convection. The governing equation of natural convection and boundary condition can be dimensionalized by dividing the parameter to these parameters. V is the velocity of the fluid, x and y. If you go to the equation, we have x, we have y, and we have x, we have y. Here actually we have u, v, we have x, we have t minus t infinity. Now it is said if we divide this value to some characteristics value like LC, which is the characteristic length of the geometry, we can dimensionalize or non-dimensionalize that governing equation. We can rewrite that equation like this by substitution of the value x equal to x star L critical and so on. And finally, we can find this equation. This equation is important. This equation is the equation that we are going to use to understand if the flow is laminar or it is turbulent. This is the Grashof number, which is dependent on this is gravitational acceleration. Besides the coefficient of volume expansion, which usually we have ideal gas, so it will be 1 by T. T is the temperature. Ts, temperature of the surface of that object. T infinity, temperature of the fluid sufficiently far from the surface. LC is a new parameter, which is characteristic length of the geometry. We can find that. We can find this LC in different table. Later we will see how we can use this LC. And now is kinematic viscosity of the fluid. So all of these information are known and you are familiar with them, and we can find them in different table. For example, G we can find it, but can we find or calculate by this equation usually. and LC as well we can find from table. So this is Grashof number, and we can check if the flow is laminar or turbulent by this equation. So the Grashof number provides the main criteria to determine whether the fluid flow is laminar or turbulent in natural convection. So for natural convection, instead of Reynolds number, we have Grashof number. And for a vertical plate, we have critical Grashof number, which is observed about 10 power 9. So when Grashof number is higher than 10 power 9, which we can calculate by this equation, for a vertical flow in contact with the vertical plate, if it is higher than 10 power 9, it is a turbulent. If it is lower than that, it is laminar flow. But sometimes we have both of the forced flow and natural flow. Like when you use a fan to cool down that egg we had in our example. Then we should consider if if you use a fan to cool down that egg, it will be, if we ignore the natural convection, it will be external force flow or external force heat convection. We have equation for that in previous sessions I told you. But if it is natural convection, we should use the equation which I will introduce you in this session. And sometimes we have both of them. How we can consider which the flow is natural or it is forced? Because sometimes also we have wind. Wind is not created by the any pump or fan. So how we consider if the wind is cause a external flow or not? If we can ignore that or not? We can use this relationship. Grashof number divided by Reynolds number squared. If it is much lower than 1, it means that the natural convection effects are negligible. If that value is much higher than 1, it means that forced convection can be negligible. And if Grashof, this value, Grashof divided by squared Reynolds number is almost equal to 1, we have both of them. We cannot ignore each one of them. We should calculate both of them. The heat transfer due to natural convection heat transfer and also forced convection. You can see also in this figure an example. This is natural convection, no external forced flow or no forced flow, but here we have forced convection, and we can ignore the natural convection. You can see that mainly the convection is due to this external forced flow. And when we have something like this, we have still a fan, but the fan is not that much powerful to have 100% or near that forced convection heat transfer. So in this case we have both of them. Natural convection due to the buoyancy forces and temperature difference between the object and fluid around that, and also due to this flow which comes from the fan. So here we have mixed convection. To know that, we should calculate the Grashof number and Reynolds number. Then we can understand if it is only natural convection or it is forced convection, or we should consider both of them. Okay, now we have introduced the reason for this natural convection. I told you we have, similar to the forced flow, we have the laminar and turbulent flow. Now we are interested to calculate the heat transfer or rate of heat transfer due to this convection. As usual, we need to have this h, which is the convection coefficient. So to calculate this h, again we need the Nusselt number. So from now we are going to calculate the Nusselt number for different geometries. This natural convection heat transfer on a surface depends on the geometry of the surface and its orientation. So geometry of the surface, it is plate or cylindrical or anything else, and its orientation, its angle, for example, with the angle of its surface with the fluid flow, and the variation of temperature on the surface as well, at the surface as well. And also it depends on the thermophysical properties of the fluid, like K, or thermal conductivity of that, like its dynamic viscosity, and so on. So these are parameters which are affecting on this natural convection heat transfer on a surface. The simple empirical correlation for average Nusselt number for natural convection can be calculated by this equation. Nusselt number equal to HLCK. If you remember, for the forced convection, this was D, HDK. Here we have LC, or characteristic lengths. Characteristic lengths can be found in the table. It is different for different geometries, and we can find it from the table for different geometry. So this is the first difference, and also it can be guessed. This is the simple equation. C is a constant times ratio of number times the Prandtl number, power n. Or we can write C RA power NL. This RA is Rayleigh number. This is also new. Rayleigh number is equal to, just substitute this, Grashev number times Prandtl number. We call this Rayleigh number, which is a characteristic of the fluid action, which is a characteristic which we can use to find this Nusselt number. So the value of n is usually 1.4, this n, for laminar flow, and 1/3 for turbulent flow. So by the Grashev number, you can understand if the flow is laminar or turbulent. When you understand it is laminar, you should put n 1 divided by 4, and if it is turbulent, you should put 1 divided by 3. And the value of the C and the, sorry, just a moment. Sorry. So for the turbulent flow, you should put 1/3 for n, and C is a constant which normally is less than 1, is constant. And this is also important. All fluid properties like this, beta, all of them should be evaluated at the film temperature. Film temperature means the temperature of the surface plus temperature of the fluid far from the surface divided by 2, or the average temperature actually. Okay, so for example, for the vertical plates, one of the geometries we may have for this natural convection, for a vertical plate which Ts is constant, temperature of the surface is constant, we should go to table 9.1. Okay, let's see. This is table 9.1. You can see this is a empirical correlation for the average Nusselt number for natural convection over different surfaces. As I told you, in that equation, in this equation, for Nusselt number, we have LC, or characteristic length. We can find in this table. For vertical plate, the LC is equal to L, the length of that vertical plate. What about Nusselt number, which you should use? It depends on the range of Rayleigh number. Do you remember Rayleigh number? Rayleigh number I introduced here. So you should calculate the Rayleigh number. Then according to its value, which is between 10 power 4 to 10 power 9, you should use its appropriate Nusselt number. If the Rayleigh number is between these two values, you should use Nusselt number. But usually we just use this Nusselt number. For a vertical plate, we use this Nusselt number. This equation is valid for entire range. So it's better to use this equation to calculate Nusselt number. It's a little complex, as it's also mentioned here, but its accuracy is higher than these two equations. So when we have a vertical plate and we are interested to calculate the Nusselt number for that, we should use this equation actually. Also, it is mentioned that its accuracy in the range of Rayleigh number from 10 power -1 to 10 power 9 is very high, and we can use that accurately. And to find the characteristic of the fluid, like what we have here, like K for example, you should go to the table A15. If you remember, for example, for the air, you can find the mu, you can find this K for that, for example, for the air in that table. So the fluid properties should be evaluated at film temperature, as I told you, in this time when the heat flux is constant. So when we have a flat plate, vertical plate actually, and the heat flux is constant, again the characteristic of the fluid should be evaluated at film temperature. The Nusselt number relation for the constant surface temperature and the constant surface heat flux here are nearly identical. So again, you can use this equation even for the constant heat flux. But when you have a uniform heat flux, you can use a more simple equation, which is here. But we should have a definition for the uniform heat flux. Uniform heat flux means that the heat flux from this surface is same like this. You know, this is a heat which comes out from this plate. So it is uniform like this. If it is like this, for example, we cannot use this equation, okay? But when it is uniform, we can use this equation. And when we say the heat flux is uniform, when the temperature at the plate midpoint, here for example, temperature at the plane midterm T at L divided by 2 is the identical or representative of the surface temperature. Then we can use this equation to calculate the Nusselt number. Why we need to calculate this Nusselt number? As usual, you know that we need this Nusselt number to calculate the H. Then by knowing the H, we can use that Newton law for cooling to find the heat transfer. Okay, so this table is important. Table 9.1 is important to calculate rate of heat transfer for different geometries. You can see here we have for vertical plate, we have its characteristic length. We have the Nusselt number value for them. For the inclined plate also we have. For the hard surface also we have when the top of that is hot, when it's bottom of that is, or lower part of lower surface of that is hot surface. And also for vertical surface, when we are interested to know the heat transfer from its sides and horizontal cylinder. Even for a sphere, we have these characteristic lengths and we have these Nusselt number values for different Rayleigh number. So this table is important when we have different problems. Okay, class, any wonder?
Yes, doctor.
Okay, thank you. Okay, can you see the PowerPoint?
Yeah.
Okay, thank you. I will just solve 3 examples, then I will inform you about next session. Let's just see some example of what I told you today. Okay, the first problem is about heat transfer of a cylinder. Let's see what is the question. A 10-meter long section of a 6-centimeter diameter horizontal hot water pipe passes through a large room whose temperature is 20 degrees Celsius. So we have a pipe, we know its dimension, and we know it is horizontal. It is important. You know, here when you are dealing with the natural convection, its orientation is very important. So it is horizontal and it contains hot water. So the fluid is inside the pipe is water, and it is hot water. In other words, its temperature it's higher than the temperature of the surrounding. Sorry, just check if it is recording. Yes. Okay, so if the temperature and the emissivity of the outer surface of the pipe are 70 degrees Celsius and 0.8 respectively, so we know the emissivity of the pipe surface, which is 0.8, and also we know Ts, the surface of the temperature of the outer surface of the pipe, which is 73 degrees Celsius. Now we should determine the rate of heat loss from the pipe by natural convection and also by radiation. Here we can also calculate the heat loss or heat transfer by radiation because we have the emissivity. Okay, first let's see which type of the convection we have. It is mentioned here, the natural convection, but we can guess also from the question that there isn't any fan, there isn't any source to push the flow. So we have only natural convection. To calculate heat transfer, again we should use okay, let me go here. Again, we should use this equation. This is the Newton law for convection. Okay. Again, we have, but again, we don't have this H. H is the problem when you are dealing with the question related to the convection heat transfer. Always you are going to find this H. So how we can find H? By Nusselt number. And where you can find that Nusselt number? The Nusselt number can be found in this equation, in this table, as I told you. First, let's see what is the geometry of our question. It is not vertical plate, not inclined plate, or even the surface, or the horizontal plate. It is horizontal cylinder. This is the appropriate geometry for our problem. What is the Nusselt number for that? This. But we should also check the Rayleigh number for that. And also we know the LC or characteristic length will be equal to its diameter. Okay, so from this table we know which equation we should use to find Nusselt number, and we know also how much is LC is equal to the diameter of the pipe. As you can see here, this is our pipe. We know its geometry. Its length is 10 meter, its diameter is 6 centimeter, its surface temperature is 73 degrees Celsius. We know its emissivity as well, it's 0.8. We know the temperature of the air around that, which is our T infinity. Free stream temperature is 27 degrees Celsius. And also you know that to find the characteristic of the fluid which is flowing on the object by natural convection, we should use the film temperature to find those information. So here the fluid is air. The film temperature is T infinity plus Ts divided by 2. 73 plus 27 by 2 is 50 degrees Celsius. You should go to table A15. Why table A15? Because you are dealing with air as an ideal gas. It is one of your assumptions. Air is ideal gas. If you go to table A15 for the air at this temperature and the pressure of 1 atmosphere, you can find its thermal conductivity, its kinematic viscosity, its Prandtl number, and also you can calculate this volume expansion coefficient for the, this is important, TF, film temperature. You know this equation that the volume expansion coefficient or beta is equal to 1 divided by T. But which T here? You have two different T. The T of the boundary layer or the temperature of the film or film temperature. So 1 divided by TF in terms of Kelvin. It should be in terms of Kelvin as well. So temperature of the film is 50 degrees Celsius plus 223. We will have it in terms of Kelvin. So beta is also this much. So we have all of this information, and also LC from the table I showed you. The LC is equal to the diameter. First, let's calculate the Rayleigh number. Rayleigh number by the equation also we had for that. If you remember, this is the equation to calculate Rayleigh number. Just repeat it here. Equation for Rayleigh number, gravity 9.81, beta we have calculated here, Ts we have, T infinity we have, term of Kelvin, or even here can be in term of Celsius, because this is just the difference between two temperature at Kelvin is equal to difference between two temperature at Celsius, but you can convert it to Kelvin. it's okay, but it should be defined in terms of Kelvin. And also D is the diameter of the this is actually LC in the equation. This is LC, but LC here is equal to D divided by no power 2. No, here is kinematic viscosity. We have that substitution in the equation, which gives us this Rayleigh number. So our Rayleigh number is 6 point something times 10 power 5. To calculate the Nusselt number, I showed you the equation, or equation 925 if I'm not mistaken. Yeah, actually this equation. By using that equation, we have Rayleigh number, we have Prandtl number, then we can calculate by this equation. I think you will have problem to do your calculation with this equation. Please practice by your calculators how you can easily find the answer or result of this calculation. You can see the equation is a little complex, but its result is accurate. So now we have the Nusselt number. By this Nusselt number, we had this, if you remember, H equal to, this is again the Nusselt number equal to dH divided by K. Actually, this is not D for natural. This is LC. LC times H by K. But LC here is the diameter of that. We know all of these parameters, the value for them. Then we can calculate this convection coefficient. Then we have convection coefficient, we have temperature of the surface, we have temperature of the fluid enough from the surface. What about AS? The surface of the heat transfer is the outer surface of the pipe. We can calculate it easily. Pi dl. Pi dl is the surface of a cylinder. We know the L, we know the D, then the AS is also calculated. So the heat loss by convection or natural convection is this much. What about the radiation? We had this equation. This is the Boltzmann equation to find the heat transfer by radiation. Epsilon is emissivity. It was given. How much is it? 0.8. It was mentioned. AS is again same as the convection heat transfer. The surface of the heat transfer is same. The Boltzmann constant is this much. It's a constant value, 5.67 times 10 power negative 8. Ts and T surrounding. Ts should be in terms of Kelvin, power 4. Ts, temperature of surface, is 73, and temperature of the surrounding, or it was mentioned in the question, room whose temperature is 27 degrees Celsius. Convert to the Kelvin, and by calculation you can find the radiation heat loss from the pipe. So this is heat loss by convection, natural convection, and this is heat loss by radiation. That was first example. Let's see the other example. Thick fluids such as asphalt and waxes and the pipes in which they flow are often heated in order to reduce the viscosity of the fluid and thus to reduce the pumping costs. Okay, this is just additional information. It says that, you know, about the asphalt or waxes, their viscosity, their actually flow ability, how much they can be transferred by a pump or something depends on their temperature, and you know about their viscosity or resistance against the flowing is dependent on the temperature. So if we increase the temperature of the fluid, its viscosity will decrease, and it can be flowing by a pump with lower power, because it can flow easily. So usually we use a resistant heater around in the pipe, which is being used to transfer the asphalt or even the waxes. So this is the information which is given here. Consider the flow of such a fluid through a 100-meter long pipe. Outer diameter of that is also given in calm ambient air at 0 degrees Celsius. What it is says calm ambient air, it means there isn't any wind. We don't have any forced flow. So this is also a natural convection transfer problem. The pipe is heated electrically by these heaters, and also you can see this is the temperature of that is constant due to this resistant heater. And the thermostat keeps the outer surface of the pipe constant 25 degrees Celsius. So TS is 25 degrees Celsius. The emissivity of the outer surface is given, of the pipe is given 0.8. The effective sky temperature is 30 degree negative 30 degrees Celsius. Determine the power rating of the electric resistant heater in terms of kilowatt that needs to be used. You know, here we have natural heat transfer due to natural convection between the surface of the pipe and the air surrounding that. But we use a resistant heater to keep this temperature of the pipe constant. So the power of this resistant heater should be equal to the heat loss from that to keep this temperature constant. So if we calculate the rate of heat transfer or heat loss from the surface of the pipe to the surrounding, then we can calculate it will be equal to that resistant heater power. And also we should determine the cost of electricity associated with heating the pipe during 10-hour period. So when we calculate the rate of heat transfer, we should find how much energy will be transferred during that 10-hour period. It means how much energy is required to keep the temperature of the pipe constant during that 10-hour period. Then the price, we should calculate the price for that much of energy, which is $0.09 per kilowatt hour. Okay, so again we know this is a natural convection heat transfer problem. So let's see what we have. The asphalt is going through the pipe. We know the length of the pipe, we know its diameter, we know its surface temperature, we know its emissivity, and we know the T sky. We'll see why it is important. And also T infinity, which is 0 degrees Celsius, the surrounding temperature. Okay, to calculate the natural convection heat transfer, again we should go to the table, to this table. Again we have this condition. It is a horizontal cylinder. Then again, to calculate the Nusselt number, we should use this equation, and also we should D as a characteristic. Okay, and as usual let's start from the end. We are going to use this equation to find the heat loss or rate of heat transfer. We know Ts, T infinitive, and As, but we don't know the H. To find H, we should use this equation. And to use this equation, we need LC and Nusselt number and K. K should come from the table A15, which is a characteristic of the fluid, which is around the object, or fluid which is taking part in the heat transfer process. And also LC is the D here actually. And what about Nusselt number? Nusselt number, according to that table, we should use this equation to in this equation we need to know the Rayleigh number, and Rayleigh number can be calculated by this equation. And to find the result of this equation, we need some information like Prandtl number, kinematic viscosity, and expansion volume coefficient. Okay, again, this is important. Film temperature. We should go to table A15 and find the characteristic of the air at 1 atmosphere and this temperature, which is film temperature, Ts plus T infinity divided by 2. Ts, temperature of the surface, is 25. Temperature of the air surrounding that is 0 degrees Celsius. So the T film is 12.5 degrees Celsius. Thermal conductivity for the air in this temperature is this much. Its kinematic viscosity is this much. Its Prandtl number is this much. All of this information come from table A15 for the air at temperature of 12.5 degrees Celsius. What about beta? We should calculate by this equation, 1 divided by T. Which T? Film temperature, or T of film. So we just convert to Kelvin, substitute TF, convert to Kelvin, and then we will have beta in terms of Kelvin. And according to the table I show you, LC, or characteristic length, is equal to the table. LC is equal to D. D here is D here is 30 centimeter, just or 0.3 meter. Just substitute. Know all of the information which we are required. We have here. Then we can calculate the Rayleigh number. Rayleigh number is this much. Now we have Rayleigh number. We can substitute here. We have Prandtl number. It is here. Then we can have the Nusselt number. When we have Nusselt number, we can use this equation, H equal to K divided by LC. Nusselt number K is now from the table A15. LC is equal to D, which is 0.3, and Nusselt number we have calculated in previous slide. So this convection coefficient is this much, 4.366 watt per meter squared degree Celsius. Now we can use this equation. We have H, we have Ts, we have T infinity. What about As? As is the surface of the tube or pipe. So we can calculate pi dl. This is the surface of the cylinder. L is given, D and pi is 3.14. So this is heat loss due to the convection. What about radiation? Boltzmann coefficient. Epsilon is given. As is same as here. Boltzmann constant is this much. Ts, we know that. And here something is different. T surrounding. T surrounding is negative 30 degrees Celsius, which was mentioned. T sky. actually. And after that it was mentioned separately. By substitution, by converting to the Kelvin and substitution in this equation, you can find the radiation heat loss from the cylinder, which is 80,000 something of watts. How much is the total heat loss? Is the result of the summation of natural heat loss due to the natural convection, heat loss due to the radiation, which is 29.1 kilowatts. Then we found this is the amount of energy which should be actually this is the heat loss from the pipe during that hour. Now the total amount and cost of heat loss during that 10-hour period. So we just multiply this amount of energy times time, Q dot. This is actually Q dot kilowatt of the energy times the time will give us the heat loss or total amount of heat loss. The cost, we should just multiply this amount of heat loss during that time times the value for each kilowatt. We know we have 29 kilowatt per hour heat loss times $0.09 for each kilowatt will give us the price for total heat loss, which is $26.18. Okay, this is the second problem. Now let's see the third and the last problem for today's session. We have a cylinder again, but its geometry or actually orientation is different. So have a 40 centimeter diameter. Diameter of the is given. 110 centimeter high cylinder hot water tank is located in the bathroom of a house maintained at 20 degrees Celsius. So we have a actually vertical cylinder that this is high, this is important. In previous example it was mentioned length, it was horizontal. This is high, it means that this is vertical. You can see here it is vertical cylinder. It contains hot water. We have its dimension and we know it contains hot water, and the temperature of the bathroom actually here is given, it's 20 degrees Celsius. The surface temperature of the tank is measured to be 44 degrees Celsius. This is TS, and its emissivity is 0.4 or epsilon. Taking the surrounding surface temperature to be also 20 degrees Celsius, as mentioned also here, determine the rate of heat loss from all surfaces of the tank by natural convection. Again, we should calculate for natural convection and radiation. Okay, again same question, we should find Q dot for the natural convection and radiation. For natural convection, again, we have this equation. For the radiation, we have this equation. But for natural convection, we don't have H or convection coefficient. So we are looking for that H first. Okay, to find that H, we need to find the H, we need to find Nusselt number. So first let's start to find for this geometry which equation we should find the Nusselt number. As you can see in this example, it is not mentioned in which surface we have heat transfer. So we can imagine this is a tank. We have heat transfer in all of the surfaces of that. We have the side surface, which is cylindrical. We have top surface and also the down surface. So let's go to the table. This table is our reference for the natural convection heat transfer. Okay, for the side heat transfer, it is a vertical cylinder. For the side of that, we have something like this. Its characteristic length is L, and it is mentioned here, a vertical cylinder can be treated as a vertical plate when D is higher or greater or equal to 35 L divided by ratio of value number power 1 divided by 4. Okay, so we should calculate this to understand if the diameter of the vertical cylinder is bigger than this. If it is bigger than this value, we can treat or we can consider the heat transfer for the side of this cylinder as a vertical plate, like this. For vertical plate, characteristic length is L, and the Nusselt number can be found by this equation. So first let's calculate this, compare with D. And also we know here in the table, let me tell this as well. The top and bottom of this cylinder or tank can be considered like this. That's actually a plate, horizontal plate. The top of that cylinder is like this, hot surface, and the bottom of that is like this. The hot surface is in down. Okay, so we can calculate the Nusselt number for the top of the cylinder by this. For sure, we should calculate the Rayleigh number to see which one of these equations we should use. And for the bottom of the cylinder, we should use this Nusselt number. And characteristic lengths for both of top and the bottom of the cylinder can be calculated by this equation. AF divided by PP is the perimeter of that surface actually, and A is it's a surface area. Okay, now let's see the problem. Okay, I'm not going to go to the start from the end again, you know that, but again we need the information about the air at the boundary layer, which is the flow. So at the boundary layer we have the film temperature, so we should calculate film temperature for the boundary layer, which is 32 degrees Celsius, 44 plus 20 degrees Celsius. This is because the surface temperature is 44 and the temperature of the surrounding air or T infinitive is 20 degrees Celsius. So T film is 32 degrees Celsius. Again, from table A15, you can go table A15 with for the air at temperature of 32 degrees Celsius. Find thermal conductivity, find the no or kinematic viscosity, and find the Prandtl number. And also we can calculate the volume expansion coefficient by this equation, y divided by Tf in terms of Kelvin. We have Tf here, 32 degrees Celsius, convert to the Kelvin, and finally we have beta, which is volume expansion coefficient. Okay, let's first calculate Grashof number. Do you remember this equation in the table? We should compare our D, or the diameter of our tank or vertical cylinder, with this value. This needs the Grashof number. So First, let's calculate Grashof number, which is equal to g beta times ts minus t infinitive times L power 3 divided by no power 2. We have all of this information. G is 9.81, beta is calculated here, ts is 44, and T infinity is 20 degrees Celsius, and L is 1.1. The length or the height actually here of the cylinder is 1.1 meter, and we just substituted. What about the kinematic viscosity? From the table F15, we know that. Then we can calculate this Grashof number. This is Grashof number. Then we should check if D is greater or equal to this value. Again, substitution of L, the Grashof number we calculated here, power 1 by 4, we can calculate. So you can see here the result of this calculation. This equation is 0.15 or 15, which is less than this. So this condition is satisfied. What next? We should, if we just go to table, this condition is satisfied. Then it says we should go to the vertical plate. Okay, for vertical, we can use this equation to calculate the Nusselt number, because now we imagine this is a vertical plate. So we can use this equation to calculate Nusselt number for the side of that cylinder. But first we should calculate the Rayleigh number. Okay, Rayleigh number simply is equal to Grashof number times Prandtl number. Why we use this simple equation? Because we have already calculated this Grashof number. So it times multiplied by Prandtl number gives us the Rayleigh number. So now we have Rayleigh number. We can use that equation I showed you to calculate Nusselt number. We have Rayleigh number, we have Prandtl number, then we can calculate Nusselt number, which is 170.2. Now we have the Nusselt number. This equation, as usual, we use this equation to calculate the convection coefficient. K is now from table A15. We have K here. Here is K. We know the L, or the length, which is 1.1 meter, and we have calculated Nusselt number here. So this is the H, or convection coefficient. Now we can find the heat transfer rate for the side of that tank. This is tank. Up to here we can just calculate the natural convection heat transfer rate for the side of that by this information. The AS for the side is the surface area of the side of the cylinder, which we can use this equation for that. Pi dl, surface of the surrounding or the side of the cylinder. We know the D, we know the L, and pi 3.14. We can calculate this AS. Substitute in this equation, we have all of this information. H is calculated here, AS is here, TS is 44, and T infinity is 20 degrees Celsius. So this is rate of heat transfer by natural convection for the side of that tank. What about the top of that? As I showed you in the table, the LC is equal to AS divided by P. What is AS in this case? AS is this for the top. So AS will be pi d power 2 divided by 4 divided by its perimeter. What is perimeter of this surface? Pi d. So simply the LC is equal to D divided by 4, or 0.4 meter divided by 4. So LC is 0.1 meter. Then by the information, the other information is same, only the LC is changed in this equation. For the Rayleigh number, we can calculate Rayleigh number for the top of that tank. What about the Nusselt number? We have Rayleigh number, then we have also equation for the Nusselt number. If you remember in the table, this is the table, this is the surface, the top of that is hot surface actually. Then we have calculated the Nusselt number. Nusselt number, we should compare in which range it is. And we have appropriate equation to calculate Nusselt number for that range. So here we have calculated Rayleigh number. So the appropriate equation is this one according to that table. So by substitution, this Rayleigh number, which is calculated, and the number constant, we can calculate the Nusselt number for the top of that tank. Then similar to the previous parts, we can write this H equal to K divided by characteristic length times by Nusselt number. Nusselt number is calculated here. K is come from the table A15 here, and LC, or characteristic length, is 0.1. We have calculated here. So this is the convection coefficient for top of the tank. Now the rate of heat transfer by natural convection for the top of the tank can be calculated by this equation. We have H, the S can be calculated by this, a circle, its area pi d2 by 4, and we know Ts, we have T infinity. Then we can calculate heat loss from the top of the tank by natural convection. For the bottom, we can apply same method or procedure for the bottom surface. The only difference is that if you see in this table, we have different Nusselt number, different equation to calculate the Nusselt number. So here the Nusselt number should be calculated by this equation. Then we can calculate convection coefficient by this equation, which already we have Nusselt number K from table A15. LC we have calculated for top and bottom is same because their geometry is same, and according to the table we know that. Then the H will be this much, 2.6. So heat loss from the bottom of the tank can be calculated by this. This is by convection. So total heat loss by natural convection is the summation of these three convection from the side, top, and bottom of the tank. So Q dot convection, Q dot side, plus Q dot top, plus Q dot bottom. We will have this much for the total heat loss by convection or natural convection. And also in the question is required to calculate the radiation heat loss from the tank. For this equation, actually, the AS is the sorry, I don't know why it is like that. The AS is the total surface area of the tank. So you can see here for AS we should write all of the areas. Top, bottom, and side are the surface area for the radiation heat loss. Epsilon is given 0.4, sigma is the Boltzmann constant, you can put here, and Ts is the temperature of the surface in terms of Kelvin power 4 minus temperature of the surrounding, which was also given. Temperature of the room was 20 degrees Celsius plus 273 Kelvin. convert to Kelvin just here. And result of this calculation will be the radiation heat loss from the tank. The only thing was a little confusing was the AS, which here is all the surface of the tank.